First line there wasn't copied the greatest, but all right, so implicit differentiation. This is a not a rule that necessarily needs to be memorized. It's not like your rule for the derivative of a specific type of function. It's a process. So all of the functions we have found derivatives of up to this point have been what are called explicit functions. So I realize that's kind of cut off by the hole punch. So this should say explicit. But an explicit function is when you have one variable expressed in terms of another variable. So think of all the functions you've had, and I realize that line kind of goes very nicely through the functions I included there. But all of those are a function y in terms of x. So you have y on one side of your equal sign equals everything else on the other side of the equal sign is only in terms of x. So y is a function of x is an explicit function. So an implicit function, and I realize I use the definition or how they worded it in the book, how it's defined, I guess, and they use implicitly as a word to describe an implicit function. But it's a relation between x and y. So it's where you do not have y explicitly written as a function of x. You have x and y kind of mixed together in the equation. So there's a relationship between x and y, but it's not explicit like it was in the functions we've worked with before. So I have examples. These, the way they are written, would be implicit functions because it's not just y equals something with x. So what I wanted to show you is sometimes you might be given an implicit function and you can write it as an explicit function or more than one explicit function. So if you look at x squared plus y squared equals 25, we could solve this for y. If I wanted to solve for y, I would subtract x squared. So y squared would equal 25 minus x squared. And then I would have to take the square root, and I would get a positive and a negative square root. So this implicit equation here really represents two explicit functions. One function would be the positive square root of 25 minus x squared. The other is the negative square root. Not that you would need to identify this in calculus, but you might remember this is the equation of a circle. So the positive square root would be the upper half of the circle. The negative square root would be the lower half. But you could rewrite that as two explicit functions, y equals something in terms of x. However, the second one that I have listed there is no way by hand to solve this for y without also having y on the other side. There's no way to just get y by itself. So in that case, the question is then, all of the rules we have for derivatives so far only work for explicit functions. What do you do if you have an implicit function? So that's why there's this process of differentiation. If you cannot solve for y, you can still find the derivative. What I do want to point out, though, even if your function is given this way, you are still considering y to represent a function of x. So y is still representing a function of x. You just don't know explicitly what that function is. So what I mean by that, I could write this a different way. I could write this as x cubed plus f of x cubed equals 6 times x times f of x. Okay, so y is still representing a function of x, and that's going to be important for you to understand in the implicit differentiation process. It does involve the chain rule, and why it involves the chain rule is because y is really representing a function. You don't know what it is, but it represents a function. So implicit differentiation, there's two main steps, and within that you're going to have multiple steps. But the two main steps you need to know, the first step is to differentiate both sides of the equation with respect to x. Like I said, you're assuming the equation determines y implicitly as a differentiable function of x, and that's why the chain rule will be applied. We'll talk about that. And then you are solving for dy dx, which is y prime. So if you want to write y prime instead of using Leibniz notation, that's fine. But ultimately, when you're finding the derivative, you are still trying to find the derivative of y. That's our end goal. It's just we're not starting out with y already by itself. So for example 1, the two equations I gave you above, we're going to find, I think I have both of those examples on here. I do. We're going to find the derivative of each of those with implicit differentiation. Now, within this process, any derivative rule we've learned so far applies if you need it. So we have x squared plus y squared equals 25. We're going to find dy dx. Again, that's y prime. So the first step is to differentiate both sides with respect to x. So I'm going to write it this way. I'm taking the derivative with respect to x, that's what d dx stands for, of each side of my equation. So the derivative with respect to x of x squared plus y squared will equal the derivative with respect to x of 25. And now I'm going to show more for this first one than I would normally show so you can see what we're doing. So on the left side, because I have a sum of x squared plus y squared, I'm really taking the derivative of each term. So I'm taking the derivative with respect to x of x squared and adding the derivative with respect to x of y squared, and that's going to equal the derivative with respect to x of 25. So you're just basically taking the derivative of everything on both sides, but again with respect to x. So then, derivative with respect to x of x squared, what's the derivative of x squared? 2x. Plus, I'm going to come back to the y squared. That's where implicit differentiation differs a little bit from just finding a regular derivative. But on the other side, what would the derivative of 25 be? 0. It's just a constant. So for the derivative of y squared, I'm going to write this off to the side. You are taking the derivative with respect to x of y squared. Since y is not x, the derivative is not just 2y because the variable is different. So if I write this a different way, I'm really taking, remember, y is a function of x. You just don't know what function it's representing, but y is a function of x. So I'm really taking the derivative with respect to x of a function f of x squared. And this is why you need the chain rule, because f of x, or y, is your inside function, and then that quantity squared is your outside function. Chain rule applies. So the derivative of this with respect to x, if I take the derivative of the outside, that would be 2 times f of x to the first power, or just 2 times f of x. But then I would have to multiply it by the derivative of the inside, which would be f prime of x. So if I write this back in terms of y, this is 2y, so 2y is part of the derivative, but then it's multiplied by either you write it as y prime, or you can write it as dy dx. If you want to use the Leibniz notation, it doesn't matter to me which way you write it. I tend to write dy dx so that I don't confuse y prime with y to the first power. That's why I use this notation, but whatever you want to use is up to you. So this is what I would write here when I take the derivative with respect to x of y squared. I get 2y times dy dx. So in short, anytime you take the derivative of something with y, you have to multiply it by dy dx because of the chain rule. So if this was find the derivative of y cubed, it would be 3y squared dy dx. So anytime you take the derivative of y, you have to multiply by dy dx. So, yes, which would be y prime if you'd rather write y prime. Okay? So once you've taken the derivative of everything, and this is also why you need a y prime or dy dx, is now you solve for this. Because ultimately that's what we're trying to find. So we have to solve for this. So to solve for dy dx, I need to subtract 2x from each side first. So that would be negative 2x. And then divide each side by 2y. So dy dx will equal, it'd be negative 2x divided by 2y, or just negative x over y. And that is, bless you, that is your derivative. You leave it that way. Your derivative will also be in terms of both x and y. It will not just be in terms of x. Okay, are there questions on that? I mean, you'll see other examples. This is the first one you're seeing, okay? From like here to here. Here to here. So I'm just saying because y is f of x. So I wrote it with f of x first because that was the inside, and then I changed f of x back to y. So I went from, I had y squared, I rewrote that as f of x squared. And then I used the chain rule to get 2 times f of x times f prime, and then changed f of x back to y, f prime to the derivative of y with respect to x. So I went into function notation back to y notation. I went into the f of x notation to help you understand why the chain rule is necessary, because that's your inside function. Does that answer your question? Okay, Connor?
So x squared and y squared are very similar,
Because x is already in terms of x. Like you're taking the derivative with respect to x. So when I have a term that is x, I just take the derivative as normal. But y is a different variable, and that's why it's the chain rule. Y is a function of x, so you have to multiply by the derivative of y. If you think of it this way, I could say when I take the derivative of x, then I have to multiply by dx, but that's just 1 because x is already in terms of itself, if that makes sense. I don't want to get too confusing with it, but that's why. Were there other questions before we move ahead? Part B to this example, I just included because you have a derivative that's not just in terms of x. So now if it says find an equation of the tangent line to the circle, x squared plus y squared equals 25, that's the same function. At the point 3, 4, you find the equation of the tangent line the same way. So we need the derivative, which we just found. The slope is the derivative evaluated at our point. So the only difference here is you have to plug in both the x and the y coordinate into your derivative. So the slope is going to be negative. Our x coordinate is 3, y is 4, so the slope is negative 3/4. Okay, so that's the difference, is both coordinates are plugged in because it's in terms of x and y. And then if our point is 3, 4, you can write it in point slope or slope intercept. Y minus 4 equals negative 3/4 times x minus 3. As I told you, equations of tangent lines will not go away. right, so let's move on to finding the derivative of the next function, the x cubed plus y cubed equals 6xy. Okay, so same process. You start out by taking the derivative with respect to x of both sides, or the derivative with respect to x of everything. So I'm taking the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed, and that'll equal the derivative with respect to x of 6xy. Okay, so derivative with respect to x of x cubed is what? 3x squared. Derivative with respect to x of y cubed. So you take the derivative like you normally would, 3y squared, but it's y and not x. So you have to multiply it by dy dx. Okay, because of that chain rule part. Equals derivative of 6xy. You need the product rule. Yes, you have a product. Okay, product rule still applies. So the 6 you can pair with either the x or the y. So I'll just say the first function is 6x, the second is y. Derivative of 6x is 6. Derivative of y is 1. Yep, 1 dy dx, or just dy dx. Because you're taking the derivative with respect to x. Anytime you take the derivative of y, you multiply by dy dx. It's the same reason why we multiply by dy dx here. Okay, so then with the product rule, first times second prime is going to end up being 6x dy dx plus second times first prime is 6y. Say that again. Like here. This, the d dx just means I'm taking the derivative with respect to x of this, whereas dy dx means you're taking the derivative of y with respect to x. So this actually represents y prime. This just says I'm taking the derivative of whatever I write after it. So that's why there's not a y with that one. All right, so that is taking the derivative part. The derivative part is done for both sides. Then you have to solve for dy dx. And in this case, we have two terms that have dy dx. So to solve for dy dx, you need the terms with dy dx on the same side of your equal sign, everything else on the other side. So we have to do some rearranging. So I'm going to bring the 6x dy dx over to the left, and then I have to subtract the 3x squared to bring it over to the right. So I'll have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. And the reason why I'm bringing them to the same side is because what can I do from here to solve for it? I can factor it out then. So I have dy dx times 3y squared minus 6x. I didn't change the right side. And then I can divide both sides by the quantity 3y squared minus 6x. So dy dx will equal 6y minus 3x squared over 3y squared minus 6x. And you could leave your answer that way. If you wanted to simplify, the only thing you could do is divide everything by 3. You cannot cancel these y's or these x's because they are terms, they are not factors. But everything, all 4 terms, can be divided by 3. So it'd be 2y minus x squared divided by y squared minus 2x. Questions on that one? Okay, and I tried to include some examples where different things come up. So if you look at example 3, we have find y prime, which is dy dx. Find y prime if sine of x plus y equals y squared cosine x. So I need to take the derivative with respect to x of both sides. To take the derivative of the left side. How would I do that? I need the chain rule because I have sine of x plus y. You cannot distribute sine to get sine of x plus sine of y. Okay, so don't do that. Just pointing out things I've seen happen. Don't do that. So I would need derivative of the outside would be derivative of sine. So cosine of, leave the inside the same, x plus y, and then multiply by the derivative of x plus y. So what's the derivative of x? 1 plus the derivative of y. Yeah, 1 dy dx or just dy dx. Okay, equals, what do we need on the right side? Product rule. Welcome to derivatives. So first function, y squared. Second function, cosine of x. Derivative of y squared? 2y dy dx. And then derivative of cosine of x is negative sine of x. So then, product rule, I would have a it's only when you take the derivative of something with y. So cosine of x is in terms of x. Does that help? Okay. So I would have negative y squared sine of x plus, I'm going to write this product as 2y cosine of x dy dx. Okay, and then this one, I realize we're getting close to time here, but to solve for dy dx, in order to get everything with dy dx on the same side, I actually have to distribute cosine of x plus y to the 1 and the dy dx here. So I would have cosine of x plus y plus cosine of x plus y times dy dx. Okay, and then my right side I am not changing at the moment. And then I have 2 terms then that have dy dx. I can get them on the same side, so I'm going to get those on the I'm just going to get them onto the left side and then everything else onto the right. So I would have cosine of x plus y dy dx minus 2y cosine of x dy dx equals, and it'd be negative y squared sine of x minus cosine of x plus y. And then just to get this written out, so on the left side, the dy dx would be factored out, and you would divide by what's left. So overall, I don't want to skip steps, but I want to get this written out. So I would have the negative y squared sine x minus cosine of x plus y divided by cosine of x plus y minus 2y cosine of x. And there's actually a bell today at the end of the day.